Okay, so yesterday including last week, we talked about the convergence of Fourier series representation. Okay, so in particular, in continuous time, right? When we're looking at periodic continuous time signals, we want to see when the convergence of this, summation as capital N goes to infinity, converges to the actual periodic signal x of t. Okay. Now we showed, under different notions of convergence, that almost all practical signals that we may encounter in practice would have a Fourier series representation, right? Periodic signals, I would say. Okay. So then, given the fact that most periodic signals can be written in terms of its Fourier series representation, we can then go on to analyze or compute the Fourier series representation for different types of signals, different signals. Okay, so then we looked at some common properties of these continuous time Fourier series. That gives us basic formulas for computing the Fourier series for basic operations such as addition under the linearity property, right? Time shifting, time reversal, time scaling, multiplication, conjugate symmetry, and so on and so forth. Okay, so with knowledge of these. Of the Fourier properties of the Fourier series under these basic operations, this will help us, compute the Fourier series representation for more complex signals. Right. So if you have complex signals that can be decomposed into these basic operations, then through this table, you should be able to derive or compute the Fourier series representation for the complex signals much more easily. Okay, and this is what we did for these few examples here, right? So, for example, in this 3.6, we were looking for the Fourier series representation of g of t, which is equal to the sum of x of t minus 1 minus 1/2, where x of t is the periodic square wave that we looked at in example 3.5. So by linearity property, we know that the Fourier series coefficient of g of t will be equal to the Fourier series coefficient of x of t minus 1 plus that of minus 1/2. Okay, and the Fourier series coefficient of this x of t minus 1, right, which is a time-shifted version of x of t, would then be the same Fourier series coefficient times a phase shift. Okay, so following procedures similar to this, we can utilize the properties that we showed to help us derive the Fourier series representation of more complex signals. So we did the same here by identifying the fact that the derivative of x of t gives you the g of t we showed on the previous page. Okay. All right. So that's regarding the continuous time case. Now today we want to move on to the discrete time case. Okay. So the same discussion can be done also for the discrete time case as well, right? So now suppose that we're looking at a periodic discrete time signal x of n that is periodic with period capital N. So what this means is that x of n will be equal to x of n plus capital N for all n, right? Now for a signal, right, that is periodic with period capital N, we're interested in looking at, whether or not it can be represented by a set of harmonically related complex exponentials with the same period, capital N. Okay. Now, if you recall, when we discussed this, the set of harmonically related complex exponentials, this is what we gave before, right? So for the set of harmonically related complex exponentials with period capital N, the functions would be equal to, e to the j k 2 pi over capital N times n, right? Where if you define 2 pi over capital N as the fundamental frequency omega naught, you can then write it as e to the j k omega naught n, right? And this is for all k, all integers k. Okay. But what's different from the continuous time case is that, in the discrete time case, there are only finite number of distinct signals in a set of harmonically related complex exponentials. Okay. So in fact, if your period is capital N, then there are only n distinct signals in this set, okay? Because once you go to, once you increase the index by capital N, you will get back the same function as that of the index k. Okay, so this is simple to prove, right? We proved this previously. If you substitute k plus capital N inside here, you will see that there will be a additional 2 pi term that comes out, which will be equal to 1, right, with the exponent, right? So exponential to the power j2 pi is equal to 1. Okay. All right. So in the discrete case, we're interested in periodic signals that can be represented by a linear combination of this set of harmonically related complex exponentials. Okay. In particular, that is the signal x of n that can be written as a linear combination of these harmonically related complex exponentials. Okay. And this phi k here is e to the j k omega naught n for omega naught that is equal to 2 pi over capital N. So if you substitute that inside, this is what you get. Okay, so this is the discrete time Fourier series, similar to what we get in continuous time. But the key difference here, okay, the key difference here is that, there are only finite number of distinct signals in the set of harmonically related complex exponentials in the discrete case. So instead of summing over all possible values of k, right, it is sufficient to sum only over capital N consecutive values of k. Okay, and this is denoted by this symbol here. Okay. So this denotes the set of n consecutive integers. Okay. So to apply this, discrete time Fourier series representation, right, there are two questions that you need to ask first. Right? So first of all, you need to determine when a signal x of n can be represented in terms of its Fourier series representation. Right? So in continuous time, we spent a lot of time talking about this, right? So in the continuous time case, right? It's very hard to have exact convergence, right? Convergence over all points of the function. Convergence of the of the Fourier series representation to x of t at all points of the function. So we considered other notions of convergence, such as convergence in the sense of having vanishing error energy, or convergence in terms of convergence almost everywhere except at isolated points of discontinuity, okay, which is specified by the Dirichlet conditions. Okay, so there's the same question here, right? What signal x of n has a Fourier series representation? Okay, so when you say that a signal x of n has a Fourier series representation, it means that it must be able, you must be able to write it as a linear combination of these complex exponentials. Now, each one of these complex exponentials are periodic with period capital N. So the linear combination of them must also be periodic with period N. Okay, so the first thing is that x of n needs to be periodic with period N. Okay, so to answer this question of determining if xn has a Fourier series representation, you should note that first of all, xn must be periodic with period N. Okay. But then the question is, are all signals that are periodic with period N, does all signals with period capital N have a Fourier series representation? Okay. So does all xn with period N have a Fourier series representation? Okay. Now this is equivalent to asking, is there a solution to the set of coefficients ak, right, for k in some consecutive value of n, such that this equation holds for n over a consecutive range of values. Okay, in particular, let's say such that x0 is equal to summation ak, x1 is equal to summation ak times e to the j 2 pi capital Nk, so on and so forth, up to x of n minus 1 summation e to the j 2 pi capital Nk n minus 1. Okay, so asking whether or not any signal xn with period capital N have a Fourier series representation is equivalent to asking whether or not there is a solution to a k such that this system of linear equation holds for any choice of values x0 to xn minus 1. Okay, for any okay. Okay. And the answer to this question is yes, right? Because what we have here, right, you can show that the capital N equations that you have here are linearly independent. Okay. So when you have capital N unknowns, right, you have capital N equations, linear equations, to solve capital N unknowns. Right? There must be a solution if the equations are linearly independent. Okay. So the answer is yes. Okay, since the equations are linearly independent. Okay. Do we have any questions about this part? Okay. Right. So different from the continuous time case, the existence of a Fourier series representation is much simpler to show in the discrete time case. Because if you want to show whether or not an expression of this kind, a representation of this kind holds for any periodic signal x of n, you only need to see if there exists a sequence of a set of coefficients, let's say a0 to a capital N minus 1, such that this equality holds for for any consecutive values of n. Okay, and this is true because the capital N, linear equations that you get will be linearly independent. Okay. So, right. So now we have established the fact that any periodic signal in discrete time has a Fourier series representation. Okay, so there would be no exceptions, like in the continuous time case. Okay, but then how do we find the values of the Fourier series coefficients? Okay. So the procedure is also similar, right? To determine the Fourier series coefficients, we also utilize the fact that if you sum a complex exponential over, one period, capital N, right? So if you sum this complex exponential over one period, then this summation must be 0, right? So if you recall, we talked about this previously. You can view a complex exponential as, sinusoids, right? So if you sum samples of a sinusoid, over one or more periods, then the summation must be equal to 0 because the positive part cancels out with the negative part. Okay. The only exception is when k is equal to 0, because when k is equal to 0, this exponential is just equal to 1. So you would be summing over capital N ones, and therefore the summation is equal to capital N. Okay? So by utilizing the fact that this summation of complex exponentials is equal to a capital N if k is 0 or some integer multiple of capital N and 0 otherwise, right? We can then compute the Fourier series coefficients by multiplying both sides by the corresponding, by the complex conjugate of the corresponding complex exponential. Okay. So for example, suppose we pick this e to the minus jr 2 pi over capital N. We multiply this on both sides so that we get xn times e to the minus jr 2 pi over capital N. We sum this over one period of n. And on the right-hand side, right, we have the Fourier series representation, which is ak e to the j k, but now minus r 2 pi over capital N, and again summing n over one period. Okay. So if you sort of switch the order of summation, you can write this as summation k ak summation n e to the j k minus r 2 pi over capital N. Okay. Now, if you look at this summation, you can see from the above property that this summation is 0 for all k not equal to r, right? Or that this summation is equal to, is non-zero and equal to capital N only if k is equal to r. Okay. So this reduces to AR times capital N. Okay. Well, this should hold for all R, that are integer multiples of capital N, right? So, or AR plus some integer multiple of capital N. Okay. So if you divide capital N to the other side, then you find that AR is 1 over n summation xn e to the minus jr 2 pi capital N summing n over one period. Okay. So again, if you're acquainted with linear algebra, you can view this as taking the inner product, okay, between our signal and the corresponding complex exponential. Okay. Right. So this gives you the discrete time Fourier series pair, similar to what we have in continuous time.
老师，
是
那个可以问一下问题吗？
可以。
上页这边就是你可以在就是那个 ARN 上，就是怎么变这个的？就是当 k 不等于 r 的时候嘞。
k 不等于 r 的时候，这个 summation 就是等于0。OK， 所以这一个东西，它就是说，它会等于 n when k is equal to r and 0 when k is not equal to r。OK。
那个下面那个写 AR 加 LN 是吗？是 L 吗？
对，就是任何 integer multiple of capital N。
好，谢谢老师。
OK。好，还有没有其他问题？
老师，
请说。
就是为什么那个这上面，为什么 k 等于正负 n 跟正负2n 的时候，它的 summation 也会等于大 N？
因为我们现在在看的这些是，就说是周期是大 N 的 complex exponential。所以 e to the j k 2 pi over capital N，n 这是一个周期是大 N 的 complex exponential。所以你如果说，比如说，就说我 n 加大 N 的话，这个就会回到它自己。OK， 就是比如说，你原本是 e to the j k，这个 2 pi capital N，OK， 那假设你 sum over 一个周期。OK， 那就说你想象，如果说你这个 k 是带0的话 ，OK， 你带0的话，这个就是exponential 0嘛，对不对？
可以理解。
那你如果带大 N 的话，它就是 exponential 这个 j 这个2 pi n， 对不对？那2 pi 任何整数倍的2 pi 也就等于是0。
好，可以，谢谢。
可以理解吗？
嗯
，OK。